Good afternoon, everyone. Thank you for joining us today in the fourth lectures of the third edition of the Current Topics in Heritage Science lecture series. My name is Teresa Molina, and I am a postdoctoral researcher at the Institute of Geoscience in the Spanish National Research Council in Madrid. I will be moderating today's lecture, which is presented by Laura Brambilla, and entitled Acoustic Emission Techniques Applied to Historical Vehicle Engines. Laura is head of studies and research of the Autocol Arc Conservation and Restoration in Neuchâtel, Switzerland, and she got her PhD in chemical science from the Università di Milano in Italy. And she then joined the Autocol Arc Conservation Restoration team in 2013, becoming a professor in 2017. She has been leading several research and interesting projects like cans, an interdisciplinary research dedicated to the conservation of food cans in museums and collections, AQHB project for the use of acoustic emission methods for monitoring historical vehicles, FLUIDIS and LIQUOR project dedicated to natural history collection in fluids, and right now she's currently project leader of the CORINT project, a Swiss National Science Foundation synergy research dedicated to the investigation of iron artifacts in opaque and porous media using multimodal imaging techniques. Thank you very much, Laura, for being with us today to present this interesting topic. And before I leave the floor to you, just let me remind to all our audience that they can ask questions through the chat, and they will be answered at the end of the lecture, okay? So I will just leave the word to Laura. Laura, the floor is yours. Thank you very much. Good luck.
Thank you very much, Teresa. First of all, I would like to thank a lot the organizers of these seminars for inviting me. It's really an honor for me to present you today a work that was part of my research at Autocol Arc. And that was dedicated to exploring the use of acoustic emission techniques for diagnostic and monitoring the state of conservation of the engines of historical vehicles. At Autocol Arc, we form conservators and at bachelor and master level. And we perform also research in the field of conservation and conservation science. And one of the options that our students have, and that is also one of the main focuses of our research, is about objects that are part of the technical, scientific, and horological heritage. The characteristic of this type of heritage is that most of the objects have a mechanism. Therefore, there is the possibility to put them or re-put them in function to allow the visitors to enjoy a 360 degrees experience of the object in motion. However, when we consider the put in function of an object with mechanism, there is what John Ashton and David Allam define in the 1990s as an ethical dilemma of the functional objects. It means that the reactivation of the functioning condition of an object with mechanism has to be carefully evaluated and should be performed only if the functioning does not put at risk the whole stability and health of the object. Therefore, museums have different conservation choices for objects with mechanisms, and in particular, the museum divide in two categories. those that decide for static conservation, the object is just exposed for the aesthetic values, artistic values, but is never put into function. And for example, in the case of vehicles, this choice can lead even to the removal of the engine from the vehicle, because keeping the engine means also keeping all the fluids that go with oil, lubricants, cooling liquids, fuel, and so on, that can be very tricky to maintain and very dangerous by the safety point of view. And the other option, conservation choice, is the functional conservation. The functional conservation does allow, as I said before, to reactivate the mechanism of the object, to allow the visitors to enjoy the object as it was conceived at the moment of the creation. But it allows also conservation of other functions, other know-hows, like, for example, the knowledge about the conservation of an historical vehicle. So at the beginning of the ACUME project, we decided to perform a survey. We contacted museums of vehicles, and we asked them what are the methods they use in case of reactivation of their vehicles. And we got 3 different types of answers. The first choice is a reactivation without any diagnostic before. Simply, if you consider a car, you put the gasoline, you put the key, and you start the engine. And if it works, okay. If it doesn't work, well, there is a serious risk of breakage, definitive breakage of the engine. So this is not something that we recommend, but there are some heritage institutions that are performing that. At the opposite, there is the complete removal, disassemble, and reassemble of the engine. But this operation, even if it's the safest one by the object's point of view, requires specific knowledge, competencies, but in particular, a lot of time, and therefore is very costly for the museum. And not all the museum can afford this type of conservation, and for sure not on all the vehicles of their collection. In between those 2 approaches, there is another approach that is not to disassemble completely the engine, but to perform some preliminary diagnostic, non-invasive one, for example, using an endoscope to check some internal parts of the engine. This method, of course, can allow to save a lot of time and cost, but is not infallible. So in some cases, some type of malfunctions cannot be detected with this methodology. Therefore, we wanted to propose a methodology that allow museums of historical vehicles to perform a correct diagnostic before the reactivation of the engine, that was human independent, so based on data, scientific data, and that allow to perform the diagnostic in a shorter time and therefore less expensive for the museum. And we decided to try acoustic emission techniques to perform this diagnostic. Acoustic emission is a technique that is based on the principle that some energy is released at microscopic scale when a change happens in a solid material, and this energy propagates in the solid material in form of elastic wave and can be detected by sensors that are in direct contact with the surface. This technique is used in the field of industry and even in the field of build structure monitoring to check for formation of cracks and corrosion phenomena. It's also used in modern automotive industry to check some properties of newly produced engines, such as clicking, segmentation, or combustion performances, and is also used, for instance, to detect infestation in wood objects. So we said, okay, this technique is used in the automotive industry. Can we use it in heritage of historical vehicles? We wanted to test that. And this is how the ACUME HV project was born. ACUME is an acronym for Acoustic Emission Monitoring of Historical Vehicles, and it was the first time that acoustic emission was used in the field of technical heritage. Acoustic emission is part of what is called in industry non-destructive testing techniques, which are techniques that are used to evaluate properties of materials, components, structure, and systems. And those techniques have the characteristic of being non-invasive, meaning that they can be used without causing any damage to the original object analyzed, which is also a characteristic that is very important in the field of cultural heritage, as you all know. And so we will focus today on acoustic emission. I like very much the definition that Mr. Harrington gave in 1981 of acoustic emission. This scientist was studying some properties of tin bars subject to bending, and he defined acoustic emission as a material science stethoscope, allowing to assess the quality of the material and its integrity by listening to ultrasonic waves that are generated inside the specimen when it's subjected to stress. And this, for me, is probably the best definition of acoustic emission, is the one that is also easier to understand. Like a stethoscope, you can put a sensor on a material and you can detect a series of events happening inside the solid. Acoustic emission was firstly used in the 1950s by the German scientist Joseph Kaiser, who was using sensitive electronic instruments applied to different types of metals, in particular during the formation. And it's based on the principle, as I said before, that when something happens, a change happens in a solid material, there is a sudden release of energy, and this energy travels within the solid material in form of elastic wave and can be captured by sensors that are placed in direct contact with the surface. This method or this principle can allow to detect different types of phenomena, such as the formation of cracks, some corrosion phenomena, but also the two mechanisms or two surfaces that are moving in contact to each other and that generate noise due to wear. The proportion of energy that is released by the phenomenon ongoing inside the solid material and that propagates as waves depend on the nature of the source, how localized it is, and how rapidly this release takes place. And the signal travel inside the material, but according to the nature of the material, can also be attenuated, and therefore the material nature is one of the key parameters to be taken into account when using this technique. The technique is also used in the field of cultural heritage since the 1990s and has been developed in the last decades, different application by different research groups. I suggest you to read this book that was published in 2020 by the Getty Conservation Institute and collect some general information about acoustic emission and some application to different case studies. This publication is available for free on the Getty Conservation Institute website for download in PDF. So in the field of cultural heritage, acoustic emission has been has been considered as a method that is suitable for direct monitoring of physical changes in cultural heritage in objects that are subject to external or environmentally induced loads. It can therefore be used to trace physical damages in an object in which a stress field develops due to a deterioration mechanisms. Again, if we take, for example, the formation of a crack in a wooden object, this can be due to environmental changes and can be detected easily with this technique in a completely non-invasive way. The principle is that one or better multiple sensors are put on the surface of the object to test. Those sensors are connected to data acquisition systems and, of course, to a computer and software. And those sensors can capture the acoustic emission source events, such as, again, a crack or a corrosion phenomenon. The fact to use multiple sensors allow also to localize precisely the position of the phenomenon occurring, and the principle is based on triangulation like in geography. So using 3 sensors, you can triangulate the signal and localize the source of the noise. Acoustic emission sensors are piezoelectric crystals that operate at specific frequency and sensitivities. There are different types of sensors in commerce, and you can choose the one that fit the best your application. And those sensors transform the surface motion in an electrical voltage signal, and therefore in a sort of spectrum that you can read and then interpret through different techniques. The signals recorded are characterized by the type of and of the process, the attenuation of the acoustic wave traveling through the material due to the material itself, but also by the sensor itself, the type of sensor you choose, and also the software and hardware settings. Therefore, you have to correctly choose the sensor and the setting to monitor your system. How does an acoustic emission signal look like? It is like the green line at the bottom right. So it looks like a sound measurement characterized by different energies and peak amplitudes, by different duration and rise time. Those are all parameters that you can use then to interpret your data. And you can also select a specific threshold, for example, to remove background noise if your environment is particularly noisy. So all those parameters can be in use for interpretation and can be also set during the hardware and software settings. Before carrying out any acoustic emission measurements, it's important to verify that all sensors work correctly and to calibrate them. This operation is done through a test that looks very simple but is standardized in a norm, and is called the pencil lead break. It consists in breaking the pencil lead near one sensor, and you repeat the same operation near all the sensors that you have in your system, and you check that the sensor that is near the position where you broke your lead is the one that has the highest signal, and the one that are more far have a signal that have lower amplitude. This is what it looked like. It's like the small dots in the bottom left graph. So here the system was composed of 4 sensors. Each sensor has a different color, so red, yellow, green, and blue. And you see that breaking the pencil lead near a sensor creates an answer by all the sensors of the system. And this is how you calibrate and you verify that all your sensors are perfectly working. Another important parameter to be kept in mind is that the sensor needs to have a very close contact with the surface to be analyzed to correctly capture all the signals going on in the solid surface. And there are different clamping methods that can be used. In industry, most often the sensors are simply glued on the surface, but of course in the field of cultural heritage this is not acceptable. So an option is to use rubber bands or tissue bands, like in this case, to keep the sensors in place. Or another option, this is what we use in the Akume project, is to use a magnetic articulated arm equipped with a spring that apply a strength of 10 Newton on the surface of the sensor to keep the sensor in place correctly. The 10 Newton it corresponds to 1 kilo of weight, and this is what the company that sold us the equipment suggested us to use as a strength for keeping the sensors in place. But of course, you can be creative with the methods you use to keep the sensor in the correct position. Another factor that is very important is to use a binding medium or couplants as agent that help the signal transmission. This is exactly the same principle of an echography. You need a medium that allows the transmission of the signal between the surface and the sensor. And this binding medium has also the function of intermediate when the surface you want to measure is uneven and to feel the asperities of the surface. But the problem is that, for example, this blue gel that was sold together with the sensor, tested on the painted surface of an engine, left some stains that you can see in the picture, left some whitish stains that for us were not acceptable to be present in cultural heritage objects. So this gel, even if it's the best for this type of application, could not be used for our purposes. Yeah, it's also a closer view of the surface at using a USB microscope. And we have decided to test different type of coupling agents, including some different type of gels. The Ultra Gel 2 is the blue one you saw before in the previous slide, but we also use some agar gel that are more traditionally used in the field of cultural heritage, for example, for cleaning. We use some films because we read in the literature that a film can be used as a coupling material and as the advantage of not letting any residue, for example, in a surface like this one that presents some cracks and any semi-solid material can penetrate. But our surfaces were too uneven for a film to be used as a good coupling agent. And therefore, we have tested also some greases because grease is naturally used in the field of mechanism for lubricants or other purposes. So we have tested this Miocar lubricant grease. It's a grease that is used in the field of historical vehicles as a lubricant, and didn't leave any residue on painted surfaces of engine, and gave good performances as a coupling agent. And this is what we use for our measurements. And now let's come to the case study. We have worked in close collaboration with the Musée National de l'Automobile de Mulhouse, collection Schlumpf in France. Is a museum that includes 600 vehicles, over 25,000 square meters of exhibition. It was a private collection put together between the 1960 and 1977 by the Schlumpf brothers that were industrial in the field of textile. But in 1977, they went bankrupt, and the workers of their industry discovered at that time that they had those 600 vehicles. And between 1977 and 1982, the workers that were unemployed at that time decided to open the collection to the public to create a sort what is called the Museum of Workers. Then this museum became, from 1982 on, a national museum of France. We wanted to test, to start our research choosing one specific type of engine, and we have chosen this Renault AG1. It's a engine that was selected because it's relatively simple. It has only 2 cylinders. It's very accessible even when the engine is still in the vehicle, like you can see in the picture. And the museum had 3 exemplars of the same engine, which allowed us to do some comparison of the same type of engine in different states of conservation. This vehicle was called Taxi de la Marne because in the 1910s, it was the typical vehicle that was used as a taxi in Paris. And then during the First World War was used to bring the soldiers to the front along the Marne River. And that's how the name Taxi de la Marne became. In particular, we work on this vehicle that is the inventory 2209. This vehicle was built in 1905. It was refurbished a first time at the end of the 1950s and bought by Fritz Schlumpf in 1961. It was completely restored at the museum in Mulhouse in 1995 and kept in functional condition between 2000 and 2019 when we perform the measurements. The condition report of the vehicle reported no mechanical degradation according to the maintenance follow-up performed by the museum. The compression of the cylinder was fine, and the endoscopy of the cylinder showed nothing relevant to mention. However, it was not possible to remove the engine from this specific vehicle, and therefore to do the setup of the measurement, we have used another engine identical to this one that we will call test engine in parallel. The advantage of using this test engine is that could be mounted on a bench test, and this engine that is of the AG series, so built between 1906 and 1916, was bought as a spare part by the museum from a private who refurbished it and sell it to the museum as in good working condition. This test engine was completely disassembled for performing a condition report before performing the acoustic emission test. And in fact, the condition report showed that the engine was not really in good conditions. The pistons were incorrectly mounting, the valves were leaking, surfaces were not compliant, there was a clearance of piston rods, and a lot of intervention were necessary before starting the acoustic emission measurements, including replacing the joints and complete cleaning of the parts. And here is the equipment we have used, similar to the one I showed you before in the schematic representation. We use 4 piezoelectric acoustic emission sensors connected to 4 preamplifiers. an acquisition system that is that has 8 channels, 4 for the acoustic emission sensors and 4 that can be used for other parameters to be monitored at the same time. For example, you will want to monitor temperature, or in our case, speed. And we had a laptop equipped with dedicated software for data acquisition and interpretation, and the sensor were kept in position with the magnetic arms that I showed you before. The first part of the project was dedicated to choose the location of the sensors around the engine, close to key internal contacts and to possible sources of breakdowns, also keeping in mind special constraints for performing then the measurement when the engine is in the car, and we wanted to test also different positions. And those are the position that we have selected then for all the measurements. The first 2 sensors are on the cylinder block. The sensor number 3 cover the gears of the cam system, and the number 4 the crankcase. The 2 sensors that are on the cylinder block are used to measure the noise of the ring and the noise of the valve or the pistons. The engine was moved by hand in what we call the cold test. So the engine is not started, but is moved by hand by an external crank handle. And we wanted to perform 4 rotation in 8 seconds to have a smooth and constant measurements and movement. And those measurements that you can see here show the repeatability and the regularity of the results we obtain. And as I said before, we wanted to correlate also the speed, and we add a rotational speed sensor to the system, and to be able to measure the speed of the crankshaft angular speed. And we could, in this way, correlate the movement and the measurement with specific position of the piston during the thermodynamic cycle of an engine that include the 4 steps: power, exhaust, intake, and compression. And all this is measured by the acoustic emission sensors. We have then, once that we have performed all the setup on the engine, test engine, then we perform the measurements also on the real engine of the vehicle using the same positions. And we have performed measurements without the spark plugs and with the spark plugs. So without the spark plugs is on the left, and you can see very regular movement, similar to the one I showed you before. But when we put the spark plugs on the right, so in that case there is compression. The movement is more difficult because the air is compressed inside, because the system is closed by the spark plug, and we could see some anomalies. In particular, we saw that while in the compression, in the cylinder number 1, the compression looked normal, in the cylinder number 2, there was no signal of compression, and we were wondering why we detected this. And we were wondering if we were detecting a specific degradation that was not known before. And measuring the air tightness of cylinder number 2, we detect a malfunction of the intake valve that was not been detected during the previous check. Therefore, we show already with this test that the acoustic emission can be used to detect some typical malfunction that are happening in historical vehicles engine. We have then performed some simulation of malfunction. I will not detail you too much, but we have simulated 3 typical malfunctions that are happening in historical vehicles engine: clearance of the piston pin, connecting rod failure, and wear of the rings. And all those simulated malfunction could be detected easily with acoustic emission. we have recently, last summer, also performed another type of measurement using acoustic emission, because of course historical vehicles are considered as multi-material artifacts. The engine is the probably most important part of the vehicle when kept in functioning condition, but is not the only one. And historical vehicles are in most cases composed of a lot of parts made of wood, and who say wood say also infestation. And Cecile Costa, a second-year bachelor student, during a summer internship of 2 months, could prove that acoustic emission can be used also for the detection of the presence of insects in the wood part of the historical vehicles. And now she is currently in Canada for a bachelor thesis, where she will go on testing the same technique on other type of organic materials, such as textiles and paper. Of course, until now we have spoken about signal registration, but then one has to interpret the data, and there are a lot of different parameters that can be measured and can be used for determine the state of conservation of an engine. We use mostly time-dependent parameters, but one can use also frequency, peak amplitude, duration, energy, and all this can be done using softwares or even artificial intelligence solution. We have done a collaboration with the engineering department of Neuchâtel, where they are specialized in data analysis, and they have applied some machine learning techniques to switch from the time domain to the frequency domain, and then to do clustering of the data to verify if the signal we have acquired can be grouped in categories. And this we are also doing for Cecile Costa master bachelor thesis, collaboration with the students of the engineering department treating their data. And the machine learning techniques allow to have a 90% balance accuracy for the anomaly detection and 84% accuracy for engine condition clustering of the data. But of course, these require a lot of data. We had the feeling that we had a lot of data, but for the algorithm, finally, is not so much. And of course, it requires also specific competencies that we don't have in our group. So we decided to do this collaboration with other groups. And to conclude, in general, acoustic emission can be a very powerful tool for detection and monitoring of degradation phenomena, also in the field of cultural heritage, because they are non-invasive and non-destructive. They are very sensitive, and they can be used for early stage detection of degradation phenomena, and they also allow monitoring time of evolution of some selected phenomena. However, you need to put the sensor in contact with your object. You need to use a coupling agent that does not damage the surface of your object. And the data that you acquire need then to be post-processed, and therefore you need to develop a specific expertise. And in the field of historical vehicles, the ACUME project allowed to develop a non-invasive measurement protocol for engines. We obtain repeatable measurements. It's very important to choose the correct location for the sensors if you want to detect some malfunction. It was important for us to add an angular position sensor to verify the rotation speed and to correlate it with the position of the internal mechanism and the cycle, thermodynamic cycle of the engine. And we could detect typical malfunction. However, the comparison of 3 engines of the same time show differences from engine to engine, and therefore some statistical methods, including artificial intelligence and machine learning algorithm, can or should be used to treat the data and correctly identify the differences. And with this, I would like to thank you for your attention, and I'm here for your questions.
Thank you very much, Laura, for this very interesting presentation. I hope that it serves to raise awareness of this type of heritage and, of course, to learn more about the technique. Before moving to the question and answer session, I would like to invite you to the next lecture that will be on 22 of May at the same time right now, which will be presented by Lucia Burgio, will be entitled Analysis of Indigenous American Object from the Victoria and Albert collections. So we will be waiting for you all.